everyone, another video for you. I have a demo for you, and then we're going to talk about absorbance and transmittance. Alright, so here's the first part of our demo. I have lots of different chemicals, iron 3 nitrate, copper 2 chloride, copper 2 sulfate, I have KMNO4, potassium permanganate, and then potassium nitrate. And so we are going to record the absorbance for all of these. I want you to pay attention though to the patterns. I already broke them into their ions. Alright, so I'm going to take some measurements and you're going to record. So I calibrated this guy with water already. And I've already wiped down all the sides to the cuvettes. So let's try this FeNO3. I see an absorbance of 0.066, and it's kind of this orangey yellowy color. All right, now we're going to the blue, so I need to be at 600 for complementary. Calibrate that guy. It's thinking, there we go. Calibrated, so anytime you change the wavelength, you need to calibrate with water. Let's see the copper 2 chloride, put that guy in, you can record the absorbance. 0.36364. Same color, so I don't need to calibrate again for copper sulfate because this guy's blue. Copper 2 sulfate is also blue. 0.286. All right, moving on to potassium permanganate. That is this purpley color. So we need to go complementary 560 to 600. So we'll go over 1 to 565. Calibrate that guy. Once it's at 0, we can test this potassium permanganate. There we go. .671 for the potassium permanganate. And lastly, KNO3. I'll just stick that guy in there, I guess. I don't really know what to calibrate it to because he's clear. Ooh, 0. Wah, wah. Okay, so here's what I would like for you to notice. Hopefully you recorded those observations or those absorbances for me. But a couple of things I want you to see. The coppers. Both of these were blue in color and we were able to get absorbance. So that's a pretty clear sign to me that the blue color was coming from the Cu2+, not from the chlorine or the sulfate. How about, well, I'm guessing because we saw nitrate and nitrate that nitrate is clear. So on this guy, the orangey color must be from the iron. So far, iron 3+, copper 2+, copper 2+ are producing the colors. KNO3 was clear, and so that tells me that these potassiums are probably clear. So the MnO4- must have been the color. So it's not just positively charged metals that can produce color. MnO4- is typically purple. And then notice that when we had a clear solution, we didn't get any absorbance. So just something to keep in mind that Beer's law and everything we've been working on only works if things have color, because the color is what's going to, or those molecules that produce color, those are also the molecules that are absorbing the light. All right, a couple other things to show you. So I have a red liquid here, and I want to show you why we have to use the complementary colors. So here's green light, which is complementary to red. This is just, I'm not pointing it through the beaker yet. So look at how bright that is on the wall. Now when I go through the beaker, here it is after it's been absorbed by some of the red particles. So you can see there's clearly some of the light getting absorbed, big difference. What if I use red light through the red liquid? Here it is before, here it is after. Not much of a difference for red to red. What about green? Same idea, here's my green light. Green light, not much of a difference when it goes through the green liquid. What about red? Red through the green, I can tell the brightness dims slightly. That's why we use, and we need to pay attention to the wavelengths based off the color of our solution. What if I up the concentration? So we're gonna stick with our green light. So here's my green before, here it's getting absorbed by my red solution. What if I make this much more concentrated, more darker red? Ooh, it's not even going through at all. Interesting. So we are absorbing almost all of that light. So you can see between the two, so nothing less concentrated, more concentrated. I think I see a slight green on the wall, but not much. So when we increase the concentration, we greatly increase the absorbance. And in fact, in our lab, we have to be careful that our solution's not too dark that it absorbs all the light. Otherwise, we won't register anything on the other side. Because remember, we measure the light coming in through the cuvette, and then we measure the amount of light out, and there still has to be a little bit, and the difference is how much is absorbed. So we don't actually directly measure that absorbance, we actually measure the difference, and we'll talk about that, what that is in a second. So if it's too concentrated, we won't get a good reading. So really for our cuvettes, I would say 1.5 as an absorbance, and higher is probably too concentrated. We should dilute it. Now, one more thing I want to show you. Part of that Beer's law equation is path length. So we know that absorbance and concentration are directly related, but we've been holding the path length constant, 1 centimeter for our cuvettes. What if I change the path length? So let's look. All of these are the same solution. And I know I said graduated cylinder, but I just got 2 different size beakers. Okay, so here we go before. Oh, I don't want the letters to be blocked. Okay, here we are before. Short beaker, medium beaker, so short, medium, and now let's get the mega beaker. Oh yeah, that's a big one. So hopefully let's even just go small to big. Small, check out that brightness, versus big, way dimmer. So if I increase the path length, that will also increase my absorbance. Think about it, the light's coming through. If it has to travel through much more, it's gonna be absorbed by more particles and we'll have less coming out. Okay, so path length is an impact. Luckily for us, in most of our labs, we hold it constant, but it is something to be aware of. The more it travels through, the more light's gonna be absorbed. All right, you do not need to memorize what colors each ion or element are, but it is useful to know like maybe what things are colored. So usually, just as a rule of thumb, spectator ions are not colored, like potassium or chlorine or nitrate. It's usually going to be those things that are that could be insoluble, but it is, I would say, like good to have a rough idea, so you're kind of familiar. Again, you don't need to memorize, but you should have a rough idea of what things might turn color in solution, because clear things will not work with Beer's law. So let's look at these 2 graphs. We have transmittance and absorbance. So what's the difference? Well, we already talked about the fact that absorbance is the amount of light absorbed by the sample. Percent transmittance then must be the amount of light that makes it through. So some light is absorbed, some is transmitted. So these are wavelengths. This is what we set our colorimeter to when we look at that color wheel. And when looking at a graph, if you are, instead of, like for example, let's say you don't have the color wheel in front of you, and you don't need to memorize it, but what if I gave you graphs like this and asked you what wavelength should we set our colorimeter to? Well, what we're gonna look for is we're gonna look for maximum absorbance. So we would set it probably between 480 and 520, or minimum transmittance, because we want a lot of light to be absorbed and not a lot of light to make it through for our Beer's law calculations to be effective. So maximum absorbance, minimum transmittance, that's another way besides the color wheel we can decide what wavelength to set our colorimeter to. So there is a relationship between absorbance and transmittance. So the absorbance is equal to the negative log of the transmittance. ABS is absorbance, T is transmittance. It is not percent transmittance on here like it was on the graph. So for example, if you solved this and got 0.5, that would actually mean 50% transmittance. So you have to multiply it by 100. But if you're familiar with the log relationship, here's kind of a rough idea. If the absorbance is 1.0, that means only 10% is transmitted. If the absorbance is 2.0, 1% of the light is reaching the detector. So again, it's not that you double absorbance, you double transmittance. It's a log-based relationship. So if the absorbance is 3, then only 0.1% of the light is transmitted and hitting the detector. So we talked about this already a little bit, but if you're too concentrated, if your absorbance is too high, we're going to start to get our answers like we'll suffer a little bit. So 1.5 or higher is really like we shouldn't go past 1.5 for absorbance. Then it's going to start to impact what our calculations are. So you should probably dilute. And then just another reminder, we cannot directly measure absorbance, right? Because that's looking at what the particles are essentially pulling in from the light. But what the colorimeter does is it actually measures percent of transmittance, because we know what's coming in, and then it goes through the sample. We know what's coming out. It's hitting that detector. So we can measure transmittance. And when the LabQuest gives you an absorbance, that is actually the LabQuest doing a calculation for you. So it measures the transmittance directly and then calculates the absorbance for you, and that's the readout that we're getting. So here's your first practice problem. Suppose a solution was too concentrated for an accurate reading with the spectrophotometer or the colorimeter. The concentrated solution was diluted by placing 1 ml of the concentrated solution in a 4 ml water. So that means V2-ish, because we don't forget the 1 ml that we started, so don't forget we need the total. Okay, that solution was then placed in the spectrophotometer and an absorbance was obtained and some calculations were done, and the molar concentration was found to be this. So after the dilution, that's our concentration. What is the original stock solution? So we are looking for M1. This looks just like an M1V1 to me, so pause the video. You should be able to handle this guy on your own. All right, hopefully you got 1.8 times 10 to the negative fifth as your molarity. All right, if a 0.1 molar solution of a colored substance has a maximum absorbance at 500 nanometers, so we want maximum absorbance, so that's what we'll set the colorimeter to, and an absorbance of 0.26, so 0.1 molar, this is molarity, this is absorbance, and it was 0.26. At that same wavelength, what will the measured absorbance be if it's 0.2 molar? And it's still at the same wavelength. So they're just telling me this so they know I didn't change anything between the two trials. Well, according to Beer's law, if we increase the concentration, that will directly increase the absorbance, right? It's a direct relationship. So if I double the molarity, what should that do to the absorbance? If we double the molarity, it should also double the absorbance. So 0.26 times 2 is doubled. 0.52 should be our absorbance. All right, here's where we can actually use that new equation. Spectrophotometer really measures the percent of light that is transmitted through the solution. The instrument then converts percent transmittance into absorbance. If the absorbance of a sample is 0.85, what percent of the light is transmitted? So we want to find the percent transmittance, and we know that absorbance is equal to the negative log, and that's the log base 10, of the transmittance. So I want you to try, and then I'll show you the answer. All right, don't forget to get rid of that log. We take 10, so to get t by itself, we take 10 to the negative 0.85, the negative because of this minus sign, to get our t. So we get 0.14 times 100%, so the percent transmittance should be 14%. So when the absorbance was 0.85, the transmittance was 14%. All right, here's what I would like you to do as a follow-up today for this video. This simulation link is on the agenda, so you can click the active link instead of typing that all in. And I want you to explore the percent transmittance and absorbance relationship. So for example, why don't you start, if we can adjust the concentration of the solution until you get a percent transmittance, 14%, and then I want you to see what the absorbance is. That was just the problem we solved. So let's see if the simulation matches. When you have 14% transmittance, does the absorbance match the previous problem? I would like you to see, and again, this is just you kind of messing around. Take a couple minutes for each bullet point. So even when you've done, for example, when you've done this, I still want you to mess around and see the relationship between transmittance and absorbance. Maybe make your absorbance 1, and then make it 2, make it 3. Anyways, how does changing the wavelength, so the type of light, the color of light, impact percent transmittance and absorbance? I want you to see how changing the path length impacts both. And then all of the solutions here, just a side note, are colored. Remember, clear solutions do not work. So like salt water, we saw KNO3 today, that would not work as well. So please, for really these first 3 bullet points, I would like you to take a couple minutes messing around and exploring each of those bullet points in this simulation. Awesome job, everybody.